So lucky that I've already taught this once. All right, univariate analysis involves one variable. And a bivariate analysis is concerned with a relationship between two pairs of variables. And one of the things that we had a problem with in getting our topics is they both had to be numeric. It couldn't be categorical. Do you know what I mean by categorical data?
Yes.
So, you know, your favorite pet, that would be categorical data. So population is all the measurements of interest. If you are going to be doing some sort of regression on the National Basketball League, your population would be all the players in the National Basketball League. A sample is going to be a portion of the population or a subset of that population. So let's say you're going to look at height and their number of points that they score, okay? So there's several ways you can pick your data. You can go through and you can say, you know what, and I know nothing about basketball, give me a basketball team. So you just do the Mavericks, and those are the only players you choose. Is that going to be representative per se of the population? If you want a better result, if you want better data, what should you do?
More teams.
You should take people from more teams. 2 teams?
All the teams.
Okay, so all the players in the National Basketball League would be your population. If you're going to do a good sample, then you would randomly choose people from each one of the teams. Are you with me? So if you're doing linear regression, one of the things that you want to talk about is how did you get your sample? Was it random? You know, if you choose, let's say soccer, what are you doing? Played and goal scored. So suppose he decides he's going to pick from randomly 5 people from each of the teams. All right? So he's picked goalies. He has put in defensemen. He has put in defense. We want to say midfielders and forwards. All right? So let's say that was his data set. Who are the people that usually score the goals? The forwards. So his population should probably have been what? The forwards of the National Soccer League. And then he should have chosen randomly from those teams. Are you with me? So you can talk about how you determined who you chose or what you chose on whatever data you have. All right? And that's where a lot of reflection comes in. As you do that, they say, you know, this is what I want to do, and so I started to pull players from the teams. And then I realized that, you know, the forwards are the ones that tend to score more, and therefore I narrowed my search down. Is that reflection? That's reflection from the get-go, isn't it? Okay. So now we're going to go into examples would be height and weight. Will gave us an example of the number of minutes and he played.
So I could talk about like how I didn't know anything about soccer, and then after this math investigation, I was just.
No, because you're going to say that you're an avid soccer person, that you played for the high school.
Well, then I would know that should only do the forwards, not defensemen and goalkeepers.
But that was not your first inclination. That you came up with. You don't have to be a smart soccer player. All right. So number of hours on social media and the test score. All right. Scatter diagram, a scatter plot. If you're going to do any type of regression, you will do scatter plots. It's a graph of the data points in the sample set. And this is where I got a little bit upset in the fall, and this is why I said I have to see your data and I have to see your data graph before I mark off on your topic. If I'm a scientist and I'm researching, let's say, a cure for Zika, and I come up with a hypothesis, and I collect my data, and my data look like this, am I going to waste my time any more on that research? No. I'm going to say, okay, there wasn't any correlation. How can I narrow it? What can I change? Then I might change something, And then I might get something more like this. That would at least be a little bit more reasonable to investigate because there's at least an upward trend.
You said you have more data like now?
It has to be graphed.
But I'm doing baking.
Right, but you said you would have that by Monday.
What?
Most of the bake, well, it's part of it, to see if there's a linear. We'll talk. So, are you ready? If you do this, and you see that this is your scatter plot, and you decide to continue with your IA, I want you to know that the most I'm going to give you on math will be a 2. Because to me, that shows absolutely no understanding of the use of regression. Well, that was your choice, right? Okay, so these scattered plots are used to see the possible, keyword possible, relationship between two variables that relate to the same event. Shows how much one variable will affect the other. Correlation is the relationship between the two variables. Correlation gives you direction. Either it's positive going up, negative going down, right, up, down, or no correlation, which means they're all over the place. It gives linearity, determines if points have a linear trend. There could be a correlation, and it's fine if there is. There could be a correlation that looks like this. That is not linear, that's probably exponential. Maybe that's quadratic. Maybe that is sinusoidal. But there's a relationship there. Do you scrap your IA? No. You can still put a line through it, but then you can say, and this is in your reflection, this is a curve I didn't expect. So now I'm going to use my graphing calculator and explore what type of curves may fit it best. If you want to look at how we can do fit a curve by hand to an exponential graph, then I can show you that also. Let me go back and make sure that was it. Oh, and it gives strength, okay? Your strength can be strong, it can be moderate, it can be weak, or it can be none.
I thought that was the R squared value.
Well, that correlation,
It is R squared value. So
We'll get there. This is just your overview.
What is?
All right, so if we look at what I have boxed, that strength would be 0. Okay? This strength would probably, believe it or not, be moderate to moderately strong. And this relationship would be not quite 1, but it would be very, very strong. This would be a positive strong. I've got pictures. We'll go through the pictures and stuff. All right. So here we go. A general upward trend in a pattern of dots shows a positive correlation. The value of the dependent variable increases, all right? As your x's are getting bigger, your y's are getting bigger. As the value of the independent variable increases. A general downward trend shows dots that are negative correlation. And what that is going to show is that as your x get bigger, your y's are getting smaller.
There's a limit.
There's a limit?
Yeah.
Limit to what you can do?
No, if it's a negative correlation, isn't there going to be a limit at y equals 0?
Your correlation limit is 1 and -1. It will never go above 1. 1's perfect. -1 is perfect. Negative correlation.
How about if you're graph?
Oh, yeah, you're getting closer and closer to 0. Yes. I understand. So now here the dependent variable, which is your y's, is decreasing as the independent variable is getting bigger. That is a strong correlation. Yes, sir. No, I love you, sketch. That's why you want to bring a laptop. Listen to the video. Next time I see you, anytime you come in here.
Tomorrow.
Now, Scattered points with no trend may indicate correlations close to zero. There is a zero correlation. If that is what, and that's, you have to graph your data, especially if you went online and got data, so that we knew whether or not it was even worth investigating, all right? Scatter diagrams allow us to assess the strength of the correlation. If there is no correlation, then we go back to the drawing board. All right, so this would be a strong positive, this would be a moderate positive, this would be a weak positive. Does that make sense? Is this helping? There are different amounts of negative correlation. There's a strong negative, there's a moderate negative, there's a weak negative. So not all relationships are linear. That's linear, but look at this one. That is not. That may be logarithmic. All right? But again, you can still, if you're doing the data, you can still fit a regression line, but then talk about this, and we can look to see what options you have to fit a different curve. Yes?
So you can basically do it if it's not the linear, except if it's like the scatter thing, it's like that.
Say it again.
Like if it doesn't come out linear, but it comes out like flat or something.
You can still do a linear, but then you're going to go beyond that, and you're going to work for other curves. But that you're going to do with your calculator. All right, now be careful. A correlation between two data sets does not mean that one causes the other. All right? Shoe sizes of grade school students and their vocabulary have a strong positive correlation. In other words, the bigger the shoe, the greater the vocabulary. Okay? Does that mean that the shoe size causes a bigger vocabulary?
Yes.
No, it does not. There's a confounding factor called age and years of school. The bigger your shoe size, the older you are, the more school most likely you've had, and so the more words you have been exposed to. Okay? So be careful. Do you want me to put these notes online?
Yeah.
Okay. So here's an example. So if we represent this on a scatter diagram, is the relation linear or nonlinear? You all know how to use your calculators to do this. At least get a scatter plot. How many? Who does not?
All of us. It's linear.
Anybody know?
Can you show us?
Here we go.
Is it just the y1 y2?
Uh-huh.
How'd you get that calculator on your computer like that?
It's good software. It sounds really fancy.
And it costs money.
No, it's a free one. TI would always, and they would always go to different websites as TI shut the websites down. They finally got smart and designed their own. All right, so we go to stat, and we're going to enter one. Let me go up here, it's a lot easier. So we're going to put in 1, 2, 3, 4, 4, 6.
That's broad.
What did I do?
How dare you?
What? Oh my gosh. 1, 2, 3, 4, 4. There are no 5s.
Yeah, exactly. That's what
6, 6, 6, 7, 8. All right. So then we're going to come over here, and we're going to put in 1, 3, 3, 5, 5, 6, 8, 9. Okay. So then we're going to go to second stat plot. Do you see how it says off? We're going to hit enter, and we're going to hit enter so it's on. And these are all the different graphs you can do. We're going to do stat plot. This says X's are in list 1, Y's are in list 2. And then we're going to go to zoom, and we're going to go to what's called zoom stat. So there it is. So that is why I wanted you to get data, put it in your calculator, and show me that there was some sort of relationship. Some people have done that
An
already.
exam first, the one that we had.
Because we're spending some time with
How are
you.
you supposed to get that graph onto your IA?
It's, no. There's a thing called Excel. And you put this in Excel, and Excel will grab the change. Okay, for those of you who are doing linear regression, Excel is your friend. Excel is amazing.
Certified in Excel, so I can see if you need help.
Hands loud. It's gonna be so long. I'm gonna have to do exponential regression. Yeah.
So here we go. You're just doing so.
You actually do those
What would this be called?
Oh,
Strong negative. What is this?
so correlation.
Well, there's a downward trend.
Positive. Weak negative.
Really weak negative.
Very strong positive.
Strong positive.
Weak.
Super
No, that's nothing.
Super weak two.
negative.
None. This is
Moderate weak.
moderate negative.
Moderate.
Right. Do you collect IA stuff like the data that we gave you?
The data.
Yeah, like
That, you're gonna have the data table in your paper.
I know I had graphs and I printed it out, but
I will look. Right. This could be no correlation, no correlation. You with me?
Yeah.
All right. Line of best fit or trend line is drawn on a scatter diagram to find the direction of an association between two variables and to show the trend. This line can be used to make predictions. Now, the regression line always goes through the mean point. So if you're doing linear regression, one of the things you're going to do is you're going to find how did you find your mean point. To draw a line of best fit. Now we are not going to eyeball this line. The textbook has you do that. I did not assign any problems there. But you are supposed to graph this on graph paper. You're supposed to find the mean point, and then you're supposed to guesstimate the line. That's not what our IA does. You're going to find the line of best fit. But the important thing is the mean point is calculated by finding the mean of the x's and the mean of the y's. What does mean mean?
Average.
Average. So that means you take all your x's and add them together, divide by the number of x's, all your y's, and that is your mean point. So you know what do you need to write the equation of a line?
You need a slope.
Two things,
Slope.
slope and a point. Well, guess what your point's going to be?
I mean,
The mean point. Then the rest of it is finding the slope. And there's this big long nasty equation.
doesn't Excel do line of best fit?
Oh, yeah, but you have to show the map.
And they do coefficients.
Yeah,
wait, the slope is the mean point?
you need the slope.
Wait, what's the mean point then?
The mean of
It's the average of the x's and the average of the y's. So let's look at this. If I wanted to find the mean point, x bar, which is the mean x value, would be 9 plus 13 plus 21 plus 30 plus 31 plus 5 divided by what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now you will not do the ... right? On your papers you would write y bar is equal to 260 plus 320 plus 420 plus, and you write all these numbers out and not the ... to 300 divided by 11. I'm going to do an example that has less data. You with me?
I don't understand what the mean point is.
The mean point is the average, the
Yeah, but
x value is the average of the x's and the y value is the average of the
no,
y's.
it's like, why do you need it?
Okay, when you write the equation of a line, what do you need?
Minus one.
You need one point and slope, and the point you will use for the line of best fit is always the mean point. That's why you need it.
It's a stupid correlation. Because, like, of course there's going to be a relationship. 9 calories per gram.
Okay, well, anyway, they're investigating this. Maybe this person wanted to be a nutritionist. Maybe this person decided they wanted to lose weight. Who knows? There's another example, and we'll do more of these next year. I'm looking for that's the goal of what you need now. All right, so raw data rarely fit a straight line exactly. In the real world, it is not perfect, okay? You must be satisfied with rough predictions. Typically, you have a set of data whose scatter diagrams appears to fit a line of best fit. The equation of the line of best fit is also called your regression line, and it can be used for prediction purposes. This is important. The regression line can be used to predict values within the data set. That's what it's for. It's called interpolation.
Can't extract.
This is good, okay? The regression line is not a good predictor about values beyond the data set. This is called extrapolation.
It's not spelled right.
I didn't spell it right. Extrapolation, all right? So, if your goal was to write the equation of a regression line, let's say for home price sale or prices of homes and over the last 30 years. And what you want to do is you're thinking in 10 years you're going to be buying a house. What can I expect housing prices to be? So you're using from now 30 years ago, any year within that, the line is good predictor. But it's not a good predictor for the future. What's a prime example of that?
Housing crash.
The housing crash. We had not had a housing crash like that, I don't think, ever. But yeah, all of a sudden homes were dirt cheap. That used to be extremely expensive. So you can't predict what the future holds. So if you're choosing to do that, it's part of your reflection. That you know that you're going out on a limb. Suppose we've got 14 kids in here. Suppose people start getting sick, right? You start with one kid. And then all of a sudden there's this curve, and all of a sudden we're here, and now there's 6 kids sick. Does it make sense to continue, let's say, an exponential curve? Because there's eventually everybody's going to be sick, and then it's going to level off. So the future is an issue. All right. So you've got a break.
Oh, shoot, Cass, like
All right. So this was another example of find the mean point. All right. So we needed mean point, but here they just want you to guesstimate. We don't want to guesstimate. All right. So, if you want to interpret, study was done, and this might, if you're doing regression, this might be something that you might want to do. A study was done to investigate the relationship between age, X, and time in which the child can run a kilometer. Data from the children between 7 and 18 was collected. What? Oh.
yeah, 28-year-old child.
All right, so it's 18. So the question is, here's your slope. It's -1/2. This is change in y over change in x. Well, what are the y's? Y is time. This is minutes. What is x? Age.
I don't know which one's mine.
So I would probably redo this as -0.5/1. So for each additional year, the time it takes for them to run a kilometer is decreasing at a half an inch per year. Make sense?
Half a minute.
Half a minute per year. That doesn't make sense. Okay. Are you with me there? Now, if you want the y-intercept, this says when the child is born, they can run a 20-minute kilometer. So be aware that sometimes the y-intercepts make sense. Okay? So that's one of those things you can talk about in your...
Is it wrong if it doesn't make sense?
No, it's not wrong. When a child is... Okay, so we did that. Okay, so biologist wants to study the relationship between the number of trees per hectare and the number of birds. Calculates this. So we got 5.4. Y is number of hectares. It is...
Is it like
It's a unit. I think it's bigger than an acre.
weird?
So this is number of birds. So, what does this say? This says that for each, let's see, the function below, oh, that's something else. All right, so if we want to talk about this, X is the number of hectares. Just kidding, I just did that wrong.
Started this year with birds and we're ending with birds. Deadly.
Yeah,
Now it's alive. It's like a symbol of like our journey.
yeah.
Like birds.
From death to life.
So this is how we would interpret it.
No.
Wait, it's X over Y?
No, it's x is hectares. So that means with each additional hectare, you would expect to have
That many words.
5.4 birds.
5 additional birds. The 8 means that when there are no, and this is the number of trees, okay. So for each additional tree per hectare, you can expect 5.4 more birds like trees, right? So, no. So when there are no trees on a lot, there's birds.
They like grass birds.
I should be. You like what kind of birds?
They're grass birds.
Grass birds? Yeah, they might be looking for worms. All right, moving on. So let's look at residuals. Another way to improve our line is involving residuals. This is the actual data point. This is if I were to substitute x into my regression equation, okay, and find the difference, that's the residual. All right, we take the actual point minus the point on the line. So if the residual is above, it's positive. If it's below, it's negative. If it goes through it, then it's 0 because there's no, it's equal to. The two y values would be equal. All right. To get a residual, you take the actual data y value, yi, and subtract it from the predicted y value, yp, and that is the y on the regression line. You know, one of the kids did his regression line and looked at the data and said, you know, whatever, this y value is bigger than its corresponding x value. So let's say that the x-axis are the number of people killed by cops that are white, and the vertical line is the number of people killed by cops which are African American. So at this point, this is saying that there are more African Americans being killed by cops than white people at this point. This one, more white people are being killed than African American because they're below the line. So if most of the data is here, then we can conclude that it appears that more white people are being killed by cops than African Americans. He did a study. It was quite interesting. All right. So then we go into the equations of the regression line. The least squares line uses you know this well, right? It's the one that has the smallest possible value for the sum of the squares of the residuals. So we want these distances to be, the squares of these distances to be as small as possible. That's what we mean by least squares line or regression line. All right. So the formula to find these, to find this gradient, remember, where do we get our point? Where do we get our point? It's the mean point. That's the average of the x's and the average of the y's. Gradient. All right, that is the European word for slope. Get used to it. They never use the word slope. Yep.
It's the gradient of the
Gradient
line.
Mm-hmm. So the slope is s sub xy over s sub x quantity squared. So now the question is, what do those mean? Remember, it said you must define your variables. The summation just means to add. So what does this mean right here? What are you supposed to do with x and y? Multiply them. And what are you supposed to do with all those products then? Add them. What is this telling you to do? Add the x's. What is this telling you to do? Add the y's. And then you divide by the number of numbers. That's how you get your s sub y. Now, the denominator is the s sub x quantity squared. So what is this saying? Square all the x's and then add them up, whereas this is saying what?
Add all the x's and square.
Add all the x's, get one single number, and square that number. So one of the things you need to do is to be able to define all those pieces. It's going to be online. I'm going to post these notes, PDF. Pardon? What is this? Okay. This is how you find the slope of your regression line.
Oh, that's the slope.
So this is explaining how do you get the numerator of your slope, and this is explaining how you get the denominator of your slope.
What's
N is the number of data points. So you would need to define all those, pardon? So I will post this PDF online. It might still have the misspelled
Isn't
words.
that just x bar and y bar? The sum of all the x values divided by the number of values?
What, this right here?
Yeah.
That is the product of, well, that's the sum of the x's times sum of the y's divided by n. X bars is just sum of x over n.
Yeah, so couldn't you separate that into sum of x over n plus the sum of y over n?
There's no addition. You can't multiply it or you have n squared. Okay? So let's try to do an example. When finding the least squares regression equation, remember you need to find the mean point. Then you need the slope. So here we are. I've got, how many ordered pairs do I have? 3. I like it. All right. So the first thing we're going to do is find the mean point. That would be 2 plus 3 plus 4 divided by 3. So we got 5 plus 4 is 9. I think that's 3. Y, you got 4 plus 5 plus 8 divided by 3. So I think that's 17/3. Am I right? So the ordered pair that you're going to use to write the regression equation is 3 17/3. Was that hard? Okay. So notice my table. You're going to have a data table that has all your data in it. Then you're going to go to your Excel spreadsheet. My suggestion, when you go to your Excel spreadsheet, is that you use an Excel spreadsheet. Type in your X's, type in your Y's, and how many times are you going to double check that you typed them correctly?
2 ones.
I'd say about 10. All right? Because you get one data point off and everything's wrong. And all I can say is, there's a mistake in your data. And then you've got to change everything. So what is this telling me to do? So 2 times 4 is 8. 3 times 5 is 15. 4 times 8 is 32. Now, can you get Excel to sum this for you? Yes. That's going to be 32 plus 8 is 40. That, I think, is going to be 55. What is 2 plus 3 plus 4? 9. What's 4 plus 5 plus 8? 17. Now, what am I supposed to do? Square x. So that's going to be 4, 9, 16. And then what am I supposed to do? Add them. So that's going to be 29. So I think I have everything I need, except if I go to the next page. So what, you all copied this down, correct? What was my numerator? S, X, Y? What do I need for that? Sum of the x times y's, which was this column, 55. Then what? Minus. Sum of the x's was 9.
Times the sum of the y's.
Which is 17.
Over 10.
Just this or all of it?
Just the 9 and 6.
And how many data points do I have?
3.
And is that it?
Plus 8.
I think you drew lunch. Okay, so this is, someone get a calculator out. This is 55 minus, oh, I guess we could do 3 into 9 goes 3 times. So now it's 3 times 17, which I think is 51.
4.
All right, so that is 4. My denominator was what? S of x quantity squared. And how do we get that? Sum of the x squareds. Is that the sum of the x squareds? 29. I have the formula above it so that someone can follow. Minus sum of the x's, which is 9 squared divided by n. So that's going to be 29 minus 27, which is what? 3. So my slope then is
2.
just tell me 3.
27.
Okay, so what is my slope then? 4 divided by 2 is what? 2. So if I wanted to write the equation of the line, it would be y minus what? 17/3 is equal to slope times x minus 2.
Slope is 2, not 3.
It's just stuck in my head.
X minus
X
3.
is 3.
Better?
Why would you do
I don't know. So we get 2x minus 6 minus 17/3. This is 18/3. Oh, plus 17/3. So y is equal to 2x plus minus 1/3. Yes? Okay. So now what we're going to do is we're going to test it out.
Is that the
That should be my regression equation.
what's
I think the residuals.
is that the least squares regression?
So this is what we're going to do. So now what we would do is we take every y value, substitute it into that equation wheel, find the new y value, and subtract the data point from the
The y value of the original minus the y value of
the y data minus the y from that line, yes. Okay, so you ready? I'm going to have to come in here. I'm going to get rid of the data that I have. You know you go to the top and clear. You never delete.
There's a way to do residuals on your top.
Yeah, I don't know how to do that. So now we're going to put in 2, 3, 4. And then we're going to do 4, 5, 8. So when we go to do regression line, we're going to go to stat. Now we're going to go to calculate. And what does it say? Linear regression. So we're going to choose 4. And I'm going to tell it list 1. Maybe. Second, list 1. This is not mandatory. That's the default. And then I'm going to tell it list 2. And I think I'm even going to tell it to store it in Y1. You all are good at this now. So when I hit enter, ha, look at that. What's 0.333333? 1/3. Did we do it?
Is the line
Don't you feel powerful?
is the least squares regression the same as line?
Okay. So let's talk about a correlation coefficient. To find your correlation, you might want to make this notation. You ready? Calculator. You have to turn it on. It's not on. I'm going to choose catalog, which is just above 0. So I'm going to do second 0. Now, this is alpha order. You can scroll or you can find D. Where's D? Is this D? On it.
Yeah.
So I'm going to do alpha inverse. It jumps me down to the D's. And now I'm going to have to find diagnostics on. Diagnostic on turns on the R value. So I'm going to hit enter, and I'm going to hit enter. Enter. All right. Now they're on. So now I should be able to go back to my stat, back to my calculate, back to linear regression. And this time, not only is it going to give me the linear regression, it's going to also give me the what?
Oh, that's how you get your R squared. You can do that from
Diagnostics on.
Which one is what's the difference on R squared?
Okay, we'll get there.
Wait, what is R?
R is a correlation coefficient. R squared is a coefficient of determination.
Why do we need this? Why are you so excited?
Because that tells you, the R tells you
Oh.
the strength of the correlation. All right, so we're going to get there. All right.
We have a really good one right now.
Yeah, we have an awesome one.
There's 3 data points.
Yeah. And 3 data points are not enough. That's why you have to have more. All right. So now you've seen this. Okay, so I've got some notes in the calculator. So let's go on. There's some more examples to practice on. All right. Pearson product moment correlation coefficient. Carl Pearson's the one that I guess came up with it. Denoted by R is the measure of correlation between two variables x and y giving a value between -1 and 1. It will never be bigger than 1. It will never be less than -1. It's widely used in the sciences as a measure of the strength of linear dependence between two variables. R squared explains how much of the variation from the values of y are explained by the least square regression line of y on x. I've got another slide that talks about that better. R tells you of how strong a linear relationship the data have and the direction. So R tells you strength and direction. The positive negativeness, just like on velocity, gives you the direction. And the magnitude gives you the strength.
What's the difference between r squared and r?
R squared is the square of R.
I got that.
Okay. R gives you direction because R squared is always positive. Okay? So R is going to give you direction that the R squared doesn't. The R squared I'm going to interpret in a minute. Okay? All right. So here's another thing. This is R squared is a coefficient of determination. It tells you the percent of the data that is closest to the line of best fit. In ours, it was 0.96. That means 96% of the data are very close to our regression line. If it were 20%, that means 20% of the data were close to the regression line. So look at this interpretation. If we have R equals 0.922, we square it and get 0.85. What does that mean? That means that 85% of the total variation in whatever Y represents can be explained by that linear relationship between X and Y. That also means that there's 15% of the variation in Y is unexplained. We don't know why. So that's a key what I want to say. Slide if you want to interpret what you really do want to interpret your results. All right. So perfect correlation is going to be +1. Perfect negative correlation is going to be -1. All right. It gives positive, negative, no correlation, and linearity. So strong is an R. Notice absolute value. We don't want to look at the sign because what does the sign tell you? Whether it goes up or down. So strong correlation is 0.75 to 1, ignoring sign. Moderate is 0.5 to 0.75, ignoring sign. We've got weak, which is 0.25 to 0.5. Very weak is 0 to 0.25. I wouldn't even investigate very weak. So if you're somewhere there, I'd say and you can always do a linear regression on your data. Look at your R before you start your IA to know where you are on the scale of weakness or the strength. Does that make sense? And one of their IA questions on this paper this year, they gave them a diagram, a scatter plot, and they gave them about 5 different R values and said which one is most appropriate. I know. All right. So this is an R of 7.7. This is a 0.3. So remember, we had these before, correct? The formula for finding Pearson's correlation coefficient is this. The numerator is going to be the same as your slope numerator, but your denominator is S sub x, which is this square root of what was in the denominator. And then it's going to be similar in the y's. So are you copying this down so that I can go back and we can find our correlation coefficient on our beautiful data that we match the calculator? All these years I've been getting these correlations, and it's like this weird math that's somewhere out there, and it's like, oh my gosh. So, for those of you who are not doing linear correlation, you will most likely be peer reviewing a linear correlation paper, and you have to understand all this, besides which, this is on your first test next year.
Like the first
Chapter 8, Chapter 10. No, I'll teach 8 first.
Oh, okay. Yeah,
Oh, no.
Is it what?
I'm not that mean.
Next year's easier, right?
Next year's a review of everything. And when I have time, I'll tell you just how less calculus it is. All right, let's go back.
So that's really not.
Okay, where's our gorgeous one we just did? There it is. All right, so are you ready? Now what do we have to add to our table? Don't we need an x squared or y squared column? Yes? And we need y squared? Okay, so we're going to have 16, 25, and 64. What's the sum of those? 11, 15, carry our 1, 2, 4, 105.
Wait.
What? I just added to what we already did. So I think what I'm gonna do is make room up here. Oh, okay. So let's do, have I already calculated this? So isn't s of x going to be square root of 2, or am I wrong?
Yes, so that's just defined differently.
Correlation? Okay. So what is s of x?
It's equal to the square root
Square root.
of the sum of x squared
So I square the x's and then sum them. So that'd be 29.
minus the sum of x squared, which is 29.
Again? Okay.
Over n.
Which was 3. Okay. So someone tell me we'll just leave it that way. So what is at y? Sum of the y squared, which is 105, minus
58 thirds is what that's
square root of 58 thirds. Okay, I'm just putting that. That's what I'm going to use the square root. And this should be 105 over 3.
No, it's squared.
yeah.
No, it's some of the y's and then the y's are squared.
Oh yeah. Oh yeah.
Okay, so this apparently is wrong. Oh, I don't want to do this now. All right, so we're supposed to do the sum of the x's squared, which is 81 thirds.
What did we do?
So that really was square root of 2.
What did we do?
We fixed our formula.
No, like, what did we do wrong in the first?
Oh, we took the square of the x's over n. We're supposed to take the sum of x's squared. So now I'm going to take the sum of y's, which is 17, and square it. So that's going to be 17 squared over 3. So what's 105 and minus 17 squared over 3 in fraction form?
Twenty-six over 3.
26 over 3. So now, what are we supposed to do with this? We're supposed to take the sum, the numerator from our, are we supposed to take our s of xy, which is 4?
S of xy over
Okay.
s of x times.
So now we're going to do 4 divided by, make sure you put this in parentheses, square root of 2 times square root of 26 thirds. So tell me what that is. That should be our r. Point 9607. Da, 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 da. Okay, so let's bring our calculator back up because we turned it on, right? Oh my gosh, look at our correlation coefficients. Are we smart or what?
Wait, can you go back to the
Okay, so for those who are doing linear correlations, Excel spreadsheets are everything. The hardest thing you are going to do is type in all that data. The hardest thing you do is find all that data.
How long was this to be the guide?
There's no limit. Because mathematical symbols, you can write a mathematical equation and that might be equivalent to 2 or 3 sentences if you were to write it down. And once upon a time when there were no numbers in the number system because we had to come up with figures for numbers, the math was written out in words. TWO. Stuff. Go
So
back in history.
So how long is it? When? Just like how long?
Right, there's no limit.
Is there like a minimum?
Mm-mm.
How many
Wait, are you
pages is it
serious?
usually? Like what's the average?
What number of pages?
Yeah.
I don't know, maybe 8 to 10, it depends. You know, somebody with a big data table, they might have 2 pages of data table.
Someone doing volume of revolution will have as like these things.
No, but when you do volume of revolution, you have to FOIL everything by hand.
It's not quality.
You have your math,
not
trust me.
quantity.
Foil everything by hand.
So if you have x squared plus 2x plus 3 quantity squared,
Well, that's sucker.
yeah.
But then after it's all foiled in like it's in its final form, then I can say.
Then you integrate it by hand. Show the math. All right. So I believe that is it. Do you feel like you have what you need?
Yes.
Not really.
It's not that, I mean, it's effort, but it's not like that. Just try it, let's do something fun.
Heads up, so.
Wait a minute. Let me talk to you about calculus.
Oh,